right, thank you very much. I appreciate being here. I'm very grateful to the Institute for making it possible, for inviting me to give this colloquium, and of course for inviting me to be to stay here for a whole year. I'm also wanted to say I wanted to congratulate Princeton University, as you know, because today the Nobel Committee just announced that the Nobel Prize in Physics for this year goes in some obscure area of condensed matter. To me, it is obscure, but well known to other people. And one of the recipients is Duncan Haldane at the university in the physics department. So that's exciting. All right, now I will be talking today about radiative plasma astrophysics and specifically about magnetic reconnection as a process that I will argue can power bright gamma ray flares or in general high energy flares across astrophysical systems. And this work is done in collaboration with my research group at the University of Colorado, people who are listed here, my former postdoc Benoit Cerruti, who was then a postdoc at Princeton and now is in his native France for a CNRS position, a research scientist at Colorado, Greg Werner, Professor Mitch Bigelman, whom of course you well know, and another former postdoc, Krzysztof Nalewajko, who was then a postdoc at KIPAC and now back in his native Poland for a faculty position. Right. Okay, so here's the outline of what I'll be talking about. First, I'll start by saying a few general words about plasma astrophysics and high energy emission and energy dissipation in astrophysical plasmas. Just very general things. And then I'll transition to magnetic reconnection as a fundamental physical process. And I'll give a brief introduction to what it is. And then the core of my talk will actually be this part where I will be talking about numerical particle and cell studies of non-thermal particle acceleration and relativistic reconnection in both pair and electron-ion plasmas. And then I'll argue that when applied to astrophysical systems, one really needs to be very mindful that radiation can play an important role and can, in fact, affect particle acceleration and reconnection. And I will talk about the Crab Nebula as one of the primary examples of this. All right, so first, some general things. Astrophysical plasmas are, as of course all of you know, are very complex things. They're not simple. They have thermal population of particles. They have non-thermal, significant non-thermal population, cosmic rays. All of this is bathed in radiation fields, magnetic fields, and then there are all kinds of motions, both large-scale bulk motions and small-scale turbulence. And all of these components existing simultaneously interact with each other. They exchange energy through what we call plasma processes, right? And you can see that, you know, as many components as there are, you can connect all of them in different ways. So you get a whole zoo of various processes. And studying these energy exchange processes is the realm, or essentially the definition, I would say, of plasma astrophysics. In particular, to the extent that we're interested in energy conversion, and we are, in astrophysics, of course, we're interested in explaining observations. Specifically, we want to explain why many of the astrophysical flows, including many relativistic flows, shine. We observe them from, you know, AGILE jets, pulsar nebulae, radio lobes, and so forth. They all produce light. Sometimes they produce light that is in gamma rays, very high energy gamma rays. And often, the radiative cooling time of the particles that produce this emission is much shorter than the travel time from the central object that launched this outflow in the first place, like a black hole. This implies that there must be some mechanisms of in situ local particle acceleration and dissipation, somewhere very far away from the source. And one is interested in understanding what these mechanisms are and how they actually operate. Okay, so when thinking about dissipation mechanisms, one can classify them by identifying the energy source, what carries the energy before it dissipates? And the simple classification can be thought of like this. Energy can be either bulk flow of the fluid, bulk kinetic energy, or magnetic Poynting flux. And in order to dissipate this energy, one needs to develop some sort of structure, singular structure. For example, in the case of kinetic energy, if you have sharp gradients in the direction of propagation, in the direction of the flow itself, what you have is a shock. If the gradient of the flow is perpendicular to the direction of the flow, what you have is shear, and you may have Kelvin-Helmholtz instability. And in the case of magnetic energy, the sort of quintessential primary mechanism of dissipating magnetic energy is magnetic reconnection. That requires current sheds, and this is the topic of my talk today. All right, okay, so what is magnetic reconnection? A quick detour. Well, reconnection is basically a rapid, as the name suggests, it's a rapid rearrangement of magnetic field topology. And that is basically the schematic of it is shown here and maybe illustrated in this canonical cartoon that shows what's going on. Basically, there is incoming flow of plasma from both sides, bringing oppositely directed field lines. This is the most important part, that you have to have magnetic field regions where magnetic field is oppositely directed, or at least has a component that is oppositely directed. And then these field lines reconnect at this X point right here, literally reconnect, and the magnetic tension takes them out of the system in the other direction. So you have this kind of pattern, and as I think Lorenzo Cironi, who's sitting right there, once noted, what happens here is that you bring democratic field lines and Republican field lines. It's his joke, not mine. And what do you get from this if you mix blue and red? You'll get purple, right? You'll get purple, okay. But indeed, in terms of energy, what do you get from it is you're relaxing a magnetic field configuration. The free magnetic energy that is available in this initial state gets transformed into plasma energy in various forms. And one of the key questions of reconnection research is to understand how this energy is partitioned between electrons and ions, between thermal heating and non-thermal particle acceleration, and bulk kinetic energy. Now, the key thing here is that right here, right at this point, you have transfer of magnetic flux, and that, according to Faraday's law, implies electric field. There is electric field into the plane. It is this electric field that can accelerate particles and produce all these wonderful things. Now, reconnection research has not started in high-energy astrophysics. It started in solar physics and in space physics, and there has been a large body of work on this over many decades, literally. Reconnection is now believed to be the process behind solar flares, and also behind geomagnetic storms in the Earth magnetosphere. And this process is so important that its importance has been recognized in the community, and it has been started in dedicated laboratory experiments, such as the MRX experiment here at Princeton Plasma Physics Lab, which is led by Masaki Yamada. So these experiments have contributed a lot to our understanding of this basic process. Now, if you are to kind of get a better feeling of how this happens, here is an example of how reconnection operates in the Earth magnetosphere. So here you can see reconnection happening in two places. This is the Earth, and it has a dipolar magnetic field. If the solar wind brings a magnetic flux that is directed in the different direction from the Earth magnetic field, then in this box here, reconnection may happen, and what you get is, as promised, purple field lines. Right? In this case, however, this purple comes from yellow and green somehow, magically. And then what happens here is these purple field lines reconnect back in the geomagnetic tail, and if you want to see how it happens in time, here is a beautiful movie, or animation, actually, from NASA that actually illustrates this. So these yellow lines here are just spacecraft orbits. Here is the Earth. The field lines are blue. And you can see the field lines reconnecting here are then swept by the solar wind to the backside. So the sun is shining from here. And they push together these oppositely directed lines, and they come together and result in a burst of accelerated particles. These particles travel down the same field lines and hit the Earth's atmosphere, resulting in this beautiful aurora borealis. So you can see that the Siberia burns, but Middle East at least is intact here. So you can't blame it on reconnection. Now, in addition to space physics, magnetic reconnection has been recognized in recent years as being also important in high-energy astrophysics. In fact, in all of these systems, in pulsar magnetospheres and winds and pulsar wind nebulae, in jets of active galactic nuclei, including blazars, in gamma ray bursts, and in giant magnetar flares, in soft gamma repeaters, people have invoked magnetic reconnection as the physical process powering these gamma ray outbursts. But observationally, many of the systems that I listed there have two features in common. First of all, the light that they produce, the high energy emission, is often seen to be non-thermal, having Paolo spectra, which implies non-thermal particle acceleration of the underlying radiating particles. And also, they often have very rapid variability that is sometimes even challenging to explain. For example, in blazars, we observe TeV flares with time variability on the scale of 10 minutes, which is really challenging. And the question then is, can reconnection explain these properties? And I would argue that the answer is yes. So this brings me to explaining what we think we now know about magnetic reconnection in systems like this, in relativistic systems. And in particular, what do we know about non-thermal particle acceleration? Because that's the key to explaining these flares. And I will start by talking about pair plasmas, because that's where most of the research has been done. Reconnection in pair plasmas is relevant astrophysically to systems like pulsar magnetospheres and pulsar wind nebulae. And of course, it is actually easier to study numerically than electron-ion plasmas. And the work will be described here is mostly done by Greg Werner in this paper. However, collisionless reconnection in pair plasmas and relativistic pair plasmas has been studied quite a bit, mostly with numerical simulations using particle and cell kinetic simulations by many, many people over the past 1.5 decades. And the key findings from all this research is that, first of all, pair reconnection is fast, that the incoming flows getting into the reconnection region, that corresponds to the rate at which magnetic energy can be released, can be as fast as maybe 10 or 20% of the speed of light. And another feature of reconnection is that in all reconnection, actually, not just relativistic and not pair, but in general, if you have an astronomically large system, any real size system, then these current sheets that you need to reconnect become unstable to secondary instabilities. One of them, operating in this reconnection plane, is the Turing instability that is synonymous, essentially, with reconnection. So instead of this cartoon of a nice, smooth, laminar layer, what you have is layers break up into the so-called plasmoids or magnetic islands, and they go through very convoluted and complicated dynamics. They're flying around, they grow, they merge with each other, and as a result, the process is highly time-dependent. But that's only in 2 dimensions. This is this main reconnection plane, x and y. In 3 dimensions, there is yet another instability. It's essentially the kink instability that leads to kinking of these. So in 3 dimensions, these plasmoids or magnetic islands become flux ropes, like cylinders of plasma, if you add the third dimension, they start kinking out of plane, and then they start intertwining and merging with each other. So as you can see, the process is very complex. But nevertheless, now we are in a position to study it numerically with high precision. And in particular, just in the past couple of years, several groups have made strong progress in this, including Sironi and Spitkovsky in 2014, the Los Alamos group, and us at Colorado. What we see is all of these groups see that reconnection in pair plasmas does produce robustly non-thermal particle distributions characterized by power laws. So this is what Sironi and Spitkovsky saw. This picture is a sample of spectra obtained by the Los Alamos. Now this is what I see at Colorado when I look out of my office window. It looks like this. But the actual spectrum is like this. So you can actually see that we get a lot of inspiration from the mountains. So but this is the computed spectrum. You can see it extends over more than a decade, producing a power law. With these simulations, we can then pose a practical question of, can we quantitatively characterize the properties of this non-thermal particle acceleration? The parameters of these power laws, such as, for example, first of all, the power law index. So gamma here is the Lorentz factor. That's the energy. Indeed, what we see is that if you change various parameters of the system, such as system size, and importantly, magnetization, the sigma parameter, which tells us how relativistic the reconnection process is, we see that the power law index depends on the system size for small systems, but then one reaches a certain asymptotically large system size, it no longer depends on the system size. So from this point of view, we converge. But it still depends on the sigma parameter. And the dependence of this asymptotic power law index on sigma is shown here. It's basically, all of our research shows that it basically can be relatively high for small values of sigma, so kind of non-relativistic case. And then as one goes into ultra-relativistic regime, the power law index drops, and it drops perhaps even down to 1, which is quite remarkable. So one produces really very hard spectra of particles. F is the no, this is the energy distribution function, right? So per unit energy. So this can be even challenging because this implies that most of the energy sits in highest energy particles. But in addition to the power law index, one can also ask the following question: how far do these non-thermal spectra or distributions extend? To what kind of energies can reconnection accelerate particles? That's of course a very important observational question. And we conducted a two-dimensional study with our PIC simulations at Colorado, and what we found is that indeed there is a high energy cutoff, and the cutoff energy is actually not simple, but it depends on both the system size and the magnetization in the following way, that basically it can be seen as a product of two cutoffs. One of them is a simple exponential, the other one is goes as like Gaussian, but the precise shape may not be important, but what's important is that the first one depends, this one depends on sigma. So it's basically proportional to the average released magnetic energy per particle. That's what sigma is, by the way. Sigma is kind of the Lorentz factor corresponding to the average magnetic energy per particle. But the second cutoff is actually easier to understand. It's just due to the finite voltage drop of the accelerating electric field, right? We have some magnetic reconnection with a reconnecting magnetic field B. The electric field that it produces is maybe 1/10 of B. And then there is a system size or the finite time of the reconnection process. And this gives us this kind of Lorentz factor. Right? Comparing these two cutoffs enables us to identify what we can call the asymptotically large regime, right? So we see that the cutoff depends on the system size for small systems, but then no longer depends on the system size for large enough systems. This is the condition for it. All right. Now, the results that I showed you previously were obtained with two-dimensional simulations, but of course the real world is three-dimensional, so one may naturally wonder whether things will be different in 3D. And so we started conducting a thorough comparison study with big simulations, now going into 3 dimensions. Now, 3-dimensional simulations, of course, much more expensive and much more challenging than 2-dimensional ones. And that's why we cannot really go to very, very very large system sizes. So we cannot probe, for example, the question of the high energy cutoff. But at least we can see how the general shape of the spectra and the power law index are affected by the transition to 3D. So initial conditions, in this case, it's what we call a double periodic system, where we have a thin layer. We have 2 thin layers, actually, because it's easier to handle from the point of view of boundary conditions. But basically, it's a uniform reconnecting field, like upstream field here. There is some background plasma, and then in the layer, the field reverses. It's a current layer called the Harris layer. In principle, there could be also a magnetic field component in the ignorable direction. That's called the guide field. The 2-dimensional simulations that I showed you before don't include that. But basically, we have this current layer with current providing balance in terms of Ampere's law for the magnetic field reversal. And also, this layer has a higher pressure, balancing out magnetic pressure outside. And then there are various other parameters. So you're starting with an equilibrium. Right, we're starting with an equilibrium, right. Sometimes with small perturbation just to get things going faster. The belief, though, is that things really don't depend very much on the initial conditions. They do depend on these upstream parameters and on the guide field. So for example, when we compare 2D and 3D simulations, what we see, and I think this is consistent with what the other groups see, including Lorenzo, is that the particle acceleration, interestingly, is kind of similar. It does not really change much. So for example, for these 2 cases with 2 different guide fields, so these are particle distribution functions as functions of energy, and different lines here, different symbols correspond to essentially the different extent of the box in the 3rd dimension, starting from 0, which corresponds to 2D, to larger and larger boxes, which corresponds to becoming more and more 3-dimensional. And we see that they are basically very similar to each other. However, the resulting particle spectra do depend on the guide field strength relative to the reconnecting field, which is shown here. So this can be summarized by saying that so far, at least in these relatively small systems, particle acceleration operates similarly in 2D and 3D. And I personally view it as good news, because it means that we can actually rely on 2D studies to tell us about something about the real world. And of course, we can do many more 2D studies for one big 3D simulation. So 2D studies are much better at covering large parameter space. But the particle acceleration does depend on the guide field, and in particular, a strongish guide field suppresses it. That's what we see.
Do you expect some sort of wave in this type of situation?
Well, the whole thing is, there are waves. So the whole thing is highly dynamic. We see, this is, by the way, this is just pair plasma, so many of the waves and instabilities that one may find in electron-ion plasma are not present. But even in this case, we still have kink, we still have tearing instability, and whatever is there, it's there, because it's a self-consistent particle and cell simulation. All right. Now, recently, we also started investigating relativistic reconnection and what I'll call semi-relativistic reconnection in electron-ion plasmas. So of course, pair plasmas are easier to study, and they are relevant to some astrophysical systems, such as pulsars. But many real astrophysical plasmas involve ions, electron-ion plasmas, in particular accretion disks and accretion flows on black holes, for example, and jets. Now, the particle and cell simulations or studies of electron-ion relativistic reconnection have just begun. There were not too many of them until very recently. And one thing to note from the start is that if you're really interested in ultra-relativistic regime, then there is nothing interesting there. Because in the ultra-relativistic regime, when both electrons and ions become relativistic, the rest mass of each one of them becomes irrelevant. They behave the same, and so the reconnection in this case is exactly the same as in the pair plasma case, which has been studied before. However, in many astrophysical environments, one finds conditions where electrons are ultra-relativistic, but ions are not. And this is what I call semi-relativistic regime. Right? For example, if you have equal temperatures or energy per particles, you have a huge range of average energy per particles where electrons are relativistic and ions are not. For example, this could be found perhaps in some of the black hole accretion disk coronae. And to study this, we now conducted a systematic study in 2D, in 2 dimensions with no guide field and with real mass ratio, transitioning from this semi-relativistic regime into a fully relativistic regime and seeing how things change. And here is what we found. Okay, so first of all, in terms of the basic reconnection dynamics, one of the key questions and one of the sort of outstanding questions in all of reconnection research is the question of the reconnection rate. That is, how rapidly reconnection occurs. And in collisionless reconnection, be it in the context of Earth magnetosphere or solar flares or simulations or relativistic pair plasmas, one always finds the same reconnection rate, properly normalized, of 10%, meaning that the inflow velocity is roughly 10% of the Alfvén velocity. And this is what we also find in this regime. So when we denote the reconnection rate as the ratio of electric field at the x point to the reconnecting magnetic field, that's exactly the same as the inflow velocity divided by the speed of light. We see that it changes. It depends on this sort of magnetization parameter. It becomes about 1/10 for ultra-relativistic case, as it is in pair plasmas. But for sub-relativistic case, for the semi-relativistic, when the ions are sub-relativistic, it drops significantly. But this can be accounted for essentially entirely by the dependence of the Alfvén velocity on the sigma parameter. So if one normalizes the inflow velocity not to the speed of light, but to the Alfvén speed, then one finds essentially a very weak variation. So here, this measure of the reconnection rate varies from maybe 7% to 12%, as sigma varies across like 4 orders of magnitude. So we see the same picture as was seen everywhere else in reconnection. Another interesting question, and it's particularly astrophysically important, is the question of what fraction of the released magnetic energy goes to electrons and what fraction goes to ions. This is very important, especially in systems like black hole accretion flows, because electrons efficiently radiate the energy and the ions don't. And so when we're trying to infer the energetics of the system, the energy budget, we only see radiation from electrons, and we have no idea how much energy ions get in a certain sort of reconnection process or some sort of flare. So it is important to understand this energy partitioning between electrons and ions. So what we see in these simulations is that Of course, when we are in the ultra-relativistic regime, electrons and ions behave the same, and they each one gets 50% of the energy. But then as we move into the semi-relativistic regime, where ions become sub-relativistic, and electrons still ultra-relativistic, ions get more and more energy, a larger and larger fraction of the energy. However, this does not continue indefinitely. They seem to, so this ratio seems to flatten out at about 3 to 1. So roughly speaking, ions get 3 times more energy than electrons. It's a number that does not scale with the mass ratio, and we don't yet understand why it is. However, we can fit this nice formula that describes this variation that we think can be really useful. And also, I would like to note that the same, qualitatively, the same result, that ions get more energy than electrons, but just by a factor of a few, not by a factor of square root of mass ratio or something. So this is without radiation, right? This is without radiation. But roughly the same sort of picture is seen again in the MRX experiment, for example, in non-relativistic reconnection. All right. Now, of course, our primary interest is in non-thermal particle acceleration. And what we've seen so far is that we do get robust non-thermal acceleration for electrons. Whether ions are relativistic or not, the electrons shown here, the electron distribution function is shown here in blue. In both of these are 2 different values of sigma. So this is sub-relativistic for ions, and this is kind of marginally relativistic. For ions, however, we don't really see a strong evidence for non-thermal particle acceleration. At least we cannot really claim anything at this stage. They are anisotropic, as I will explain later in my talk. Right. And just as with pair plasmas, we can attempt to study the dependence of the parameters of the non-thermal particle distributions, like the Pauli index and the high energy cutoff for electrons, on various things, in particular on this ion magnetization. So here the green line here shows where the transition between sub-relativistic ions and ultra-relativistic ions, that's sigma equal 1. And again, we see a similar picture to what we saw in pair plasma. That is, when sigma is small, the electron Pauli index is large, corresponding to very steep Pauli laws. But when sigma becomes large, the whole reconnection process becomes relativistic, and it goes down. The high energy cutoff of the electron distribution, as far as we can tell, scales again primarily with the sigma parameter. And so that the ratio of the high energy cutoff to sigma varies little across a wide range of sigmas. So here again, sigmas go over like 4 orders of magnitude. And this ratio here, this is not a log scale. This is linear scale, right? It goes from 2 to 4 maybe. So the bottom line here is that we can, these days, the computing power that is available to us allows us to really study in detail processes like this, like particle acceleration and reconnection, and quantitatively map out the dependence of the key output parameters, such as Pauli index, on various input parameters of the system. So from this point of view, I think we should expect continuing rapid progress. From this point of view, the reconnection will be essentially, I think, done in a few years in 2 dimensions, and maybe in a few more years in 3 dimensions.
Quickly, sigma less, when sigma equal 0.1, what does gamma over sigma equal?
This thing.
Less than 1, what does that mean?
Sorry. Yeah, this should be. No, this should be. This is a typo here, because this should be a sigma e, which is the mass ratio times larger. Right. Sorry. So thank you for noting. So as the sigma I is sigma defined with ions, but with electrons, we'll get sigma E here instead of sigma I. So if you look here in the small print, this is sigma E here. Yes.
You would have expected that in the limit of very high sigma I in the bottom left, the slope would go to unity.
Would go to unity. That's an excellent point, right? Here it doesn't go to unity because of the following. Because really, in order to be efficient in my presentation, I swept certain things under the rug. In particular, what this sigma is, it's a cold sigma. And the hot sigma, because by the virtue of our setup, the cold sigma is defined with rest mass energy density of ions. The relevant one is the hot sigma that doesn't increase. It sort of goes to a certain limit. And then that limit corresponds to, if you go back to that diagram for pairs, it corresponds to kind of value that you would expect. No, it's about 50 in this case. 50. So it's still large, but not very, very large. The dependence, all these dependencies are relatively slow. They go to the square root of sigma. Okay. So all of this is good. I think perhaps many people who are in this field of research will agree with me that the progress that we are doing as a community on understanding particle acceleration in processes like relativistic reconnection is rapid, and I think we will soon understand it completely, hopefully. But this means that we should really be looking for new directions, new frontiers, new challenges, and in particular those challenges that are motivated by real astrophysics. I would argue that all of these systems that I listed earlier, the systems where reconnection has been invoked as an explanation for various observed high energy phenomena. Well, they don't have to be anti-parallel, but you need to, because it's a separate question of the onset of reconnection, why reconnection does not occur all the time, but occurs only sporadically in some conditions. Right, that's a whole other lecture. No, not necessarily. I mean, sometimes you need to set up conditions for reconnection, like in the geomagnetic tail, where there is no strong guide field, and yet reconnection does not occur all the time. It occurs episodically in a bursty manner. But that's a separate discussion. Okay, but let me move on with the main sort of story here. So I would argue that magnetic reconnection, and indeed many other plasma processes that might take place in these environments, in real astrophysical environments, especially if we are to apply them to understand powerful spectacular flares of high energy radiation. They all occur in under physical conditions where radiation itself is important. And so one really needs to think about radiation from the point of view of, reconnection as a process that interacts with radiation actively. And that opens up a field of radiative magnetic reconnection. And I have to emphasize that in most of essentially almost all, the traditional research that was done on reconnection, including astrophysics, but especially so in space physics and solar physics and laboratory physics, radiation is never included. So plasma is viewed as a collection of electrons and ions, usually, or electrons and positrons, but no photons. But the energy density involved in many of these astrophysical systems, combined with the large system size, ensures that in many of these situations, radiative reaction force acting on the relativistic particles that are being accelerated becomes important. And at the fluid level, it can manifest itself as radiative cooling, affecting thermodynamics of the reconnection process, radiation pressure, radiation resistivity, Compton drag resistivity, and so forth. And all of these effects have never really been studied, and this is what we want to do. Another strong motivation to study radiative reconnection is that, after all, in astrophysics, radiation is the only observational tool that we have, the observational probe into these remote systems. So if we are to connect our underlying theories of, let's say, reconnection or turbulence or shocks with astronomical observations, we need to be able to compute the radiative signal from first principles. So we want to see how a reconnection layer literally looks like. Not just looks like, but literally looks like. What kind of light it is producing. What are the spectra and light curves of radiation, as seen by an outside observer. Not just isotropically averaged, but along a given line of sight. All right, so this is just a motivation slide. And in order to illustrate our work in this direction, I'll tell you just about one system, one project, namely the application to gamma ray flares recently discovered in the Crab Nebula. And this is actually the case where radiation is least important of all the other systems that I mentioned. Okay, so what do we know about the Crab Nebula? The Crab Nebula, of course, is one of the most studied, or perhaps the most studied objects outside of the solar system. Its spectrum is known, has been measured across many orders of magnitude. It shines across the entire electromagnetic spectrum, from radio to TeV gamma rays. And the spectrum is shown here, where the main thing is that you see is that there is this power law extending from optical to high energy gamma rays, essentially uninterrupted. This power law is synchrotron radiation. So the nebula is filled, we believe, with ultra-relativistic electrons and positrons and magnetic fields. And they produce a lot of synchrotron radiation. The particles are decidedly non-thermal, producing non-thermal power law slope in photons. There is another component in this radiation at even higher energies, at TeV energies, that's inverse-Compton, emitted by the same particles with various photon backgrounds. Now, an important thing to note here is that the synchrotron emission from the nebula extends to very high energy, but then rather dramatically drops. And it drops around 100 MeV. There is a good reason for it, as I will explain later. But surprisingly, this picture has been known for quite a while, but then surprisingly, a few years ago, actually 6 years ago already, the AGILE and FERMI spacecraft, gamma ray observatories, have detected a flare with photon energies of hundreds of MeV that falls right in this gap, right where this gap is. And this flare was remarkable for a number of reasons, but one of them is that the flare lasts about a day. That tells us that the flaring region is perhaps as large as a light day, and this is much, much smaller than the whole size of the nebula. The spectrum, this quiescent spectrum that I'm showing you here, is taken for the entire nebula. This gamma ray flare, just judging by the flare duration, is produced from a tiny region within this nebula, and in this spectral band, it outshines by far the whole nebula. So it's very, very bright, very, very short. Right? And somehow it is observed only in this energy range of hundreds of MeV and not anywhere else. We did not see any counterparts at any other wavelengths. If we think, and we do think, that this flare is produced by synchrotron emission, then we have to deduce that the Lorentz factors of these radiating particles are 10 to the 9, so peta-electron volts. And this is quite interesting because these are actually the highest energy particles we observe in the universe that we identify with a specific source, with a concrete specific source. All right. Now, however, and since then, since that September 2010 flare, there were a number of them observed. They go roughly once a year. And Anatoly just told me this morning that this morning there was yet another flare. And Fermi is now observing it as we speak. Now, the main reason why these flares are remarkable and interesting is that they present a very strong challenge from the point of view of particle acceleration. And here is the challenge. That the main challenge is how to produce synchrotron photons exceeding roughly 100 MeV. It turns out that this decline in the quiescent spectrum at this energy is not accidental. There is a good reason for it. And the reason for it is the synchrotron reaction force, the synchrotron cooling on the high energy particles. So it turns out that there is a universal upper limit on synchrotron photons, and it's very simple to understand. If you have a particle that is accelerated by some electric field, the electric force, and it moves across a magnetic field that produces synchrotron radiation. The synchrotron radiation means that particle loses energy, and correspondingly there is a drag force that acts in the direction opposite to the direction of the particle. It's given by this expression. It's proportional to the energy of the particle squared and to the square of the magnetic field. If you ask what is the highest energy to which a particle can get under conditions like this, right? You just equate these two forces, you set them equal, and you find the equilibrium, the Lorentz factor, just by comparing these two expressions. There is some maximum, right? It depends on the field strength and so forth in a certain way. But interestingly, it turns out that whereas this maximum particle energy depends on the field strength, if you combine this gamma factor with the cyclotron frequency to form the synchrotron photon energy that this particle produces in the same magnetic field, right? The magnetic field essentially cancels, and what you get is a universal constant times just the ratio of electric field to the magnetic field. So it no longer depends on the absolute value of the field, but just on the ratio of the electric to magnetic field. And the coefficient in front is literally just the electron rest mass divided by this should be divided by the fine structure constant. And it's roughly 160 MeV. Okay, so that's the conundrum. How do you produce photons, synchrotron photons, with energies higher than that? One may invoke Doppler beaming when the entire system moves relativistically towards you, but in the Crab Nebula, we don't really observe highly relativistic motions. We observe motions with maybe half the speed of light, and the required Doppler factor here is of order 3 or 4.
Why can't it be inverse-Compton?
Because you don't have enough power, you don't have enough background photons, essentially. People have looked into this and ruled it out. The synchrotron power in the nebula is much larger than the Compton power, and it's well, first of all, you wouldn't expect a short duration like this, and you don't have enough cooling, you don't have enough intensity of photon fields to produce rapid acceleration like this.
How do you know it's the nebula and not around the pulsar?
Well, that's a good question also. How do you know that it's the nebula and not the pulsar itself? We actually don't know. But it is sort of traditionally it is believed that everything that is pulsed with 30 millisecond period comes from the pulsar magnetosphere, and everything that is not pulsed comes from somewhere else, from larger distances from the nebula. So the time scale here is days, which is much larger than the time scales associated with the pulsar itself. So people just, that's actually the reason why we think it's a nebula. Of course, in this energy range, in hundreds of MeV, we don't resolve the source. So we don't know where in the nebula it's coming from. All right. Okay, but let me offer you a possible explanation. So we think that the way out of the situation is magnetic reconnection. and with the following simple reasoning, that if you take this formula at face value, we see that in order to produce photons with hundreds of MeVs, you need to relax this assumption that the electric field is less than the magnetic field. This assumption comes from kind of ideal MHD, really. So in ideal MHD, your electric field is always less than the magnetic field. But then, of course, magnetic reconnection is precisely the process that violates ideal MHD by definition, essentially. So in reconnection layers, this condition is violated, and you can have strong electric field, like in the middle of the reconnection layer, and the magnetic field goes through 0, because after all, it reverses, right? It goes from positive to negative, it goes through 0 somewhere, or at least becomes very weak. So reconnection layers, therefore, are a natural place that we can expect this to happen. And the idea goes as follows, that if you think about how particles move in the electromagnetic configuration associated with reconnection, where you have this sort of magnetic field above going this way, magnetic field below going this way, right? And there is electric field that goes in the z direction, in that direction over there. If you put an electron at this point, it will start accelerating by this electric field, and it is confined to this plane by this reversing magnetic field. So it turns out that the magnetic configuration is such that it always deviates the electron back towards the midplane. So it goes like this in this wavy pattern. This is called the Spitzer orbit. They've been studied in space physics for a long time. This is a relativistic manifestation of it. And then one can actually analytically calculate this trajectory for a simple field configuration. One can also do test particle studies that show that not only this particle gains more and more energy as it goes down the electric field, but it actually focuses more and more into the layer. So it buries itself deeper and deeper into the layer. And this is important because then it reaches a region where the magnetic field inside the layer becomes very weak, and so radiation reaction is suppressed. And then the particle can accelerate to very, very high energies. And then eventually, when it gets out of it, it radiates it in a burst. Yes?
Does it require a negligible guide field?
No, if you just add, so there is a question indeed, what does guide field do? Not only, so the guide field by itself does not affect this picture. It does affect the motion of the particle. The motion of the particle becomes spiraling like this. Now this behavior remains. Another complication, though, is that there is also this reconnected field, and that is oriented such as to deflect the particles away. So instead of one sort of going strictly along the z direction, they deviated and populate the plane of the reconnection layer in some sort of beam. Yes? Well, in this case, in the simple configuration like this, there have been studies of this. It's actually quite controversial because if you forget about like all this radiation reaction and all of that, and just study how particles move in a simple prescribed geometry like this, there was a paper by Larrabee, Lovelace, and Bisnavate-Kogan, I think, in 2003, who kind of did this semi-analytically and produced a Power law with the same slope of -1. But I'm actually don't quite understand how it's done. Sure, there is plasma flow, yeah. Well, the particle don't, it's a collisionless plasma. So a particle does not feel a flow. It just feels electric and magnetic fields, right? Yeah. It doesn't interact with the flow directly. Right, so right, that's right. So there is a, the reconnected field takes it out of this plane. But let me proceed, because I want to finish, and I wanted to show you a quick animation that illustrates sort of the key features of this process, if you permit me. I don't know how much I have, a few minutes. So animation that it's a video, so I'll show it to you briefly. It goes like this. So here is what we have, right? You have a particle that goes down the accelerating potential, and it moves away from side to side. It doesn't go along the straight line. It moves slightly to the side, but every time it turns back towards the middle. And as it turns, okay, right. Let me just quit this. I want to get to the end of my story. So as it turns, it gets into the region of higher magnetic field. It radiates. You could see these white photons, snowflakes, flying out of the from beneath the skis. It loses energy. So when it gets out of the layer a little bit, it radiates a little bit of energy, experiences drag force. And this way, it can continue with a constant speed. It doesn't accelerate indefinitely. It gets into this equilibrium. But actually what happens is that it focuses so that it deviates less and less. And then, of course, when it reaches the end, it gets into a snow pile and radiates all of its energy in one burst. So in order to study this in greater detail and more quantitatively, we've conducted PIC simulations. And these PIC simulations are different from the rest of the simulations that are done in this community because we developed a radiative particle and cell code. So most of the PIC simulations, PIC codes that exist, don't include radiation reaction force into account. My postdoc Benoit Cerruti and Greg Werner developed a radiative PIC code that includes synchrotron and inverse-Compton radiation reaction force, and actually simultaneously self-consistently computes the radiation spectra and light curves. And what we see, and by the way, this code is publicly available and people can download and use it. All right, and what we see is an example of motion of the particle that is shown here. So you can see the blue lines are these reconnected field lines and this dynamic reconnection process with multiple islands. The green dot is the particle, and the red is its trajectory. And you can see the energy of the particle and the energy of the synchrotron radiation it produces. So if you follow this, it gets here, and at this point, it travels into the plane, down the electric field. It's near the X point, and gains energy rapidly. It gains energy well above the standard radiation reaction limit. And then when it reaches this peak, it starts moving to the side and runs into the stronger field region in the magnetic island and radiates all of its energy essentially in one burst. But this burst is at photon energies higher than 160 MeV, you can see here. Right. Now, we also found by looking at the population of particles, and this is to address Russell's question, that the population of the most energetic particles is highly anisotropic, which is yet another interesting feature because most previous studies have only looked at the overall energy distribution of particles, but not at the angular distribution. So we looked at the angular distribution, and what we see is that, so these are different angular maps, similar to what you use to show galactic coordinates. They show the direction of particles in different energy beams. What you can see is that low energy particles are nearly isotropic, but the higher energy particles become more and more focused. So they focus into these beams, and the beaming factor, or the sort of the opening solid angle, decreases rapidly with the particle energy. That's shown here. This red line shows how the beaming angle depends on the particle energy. See, it's for the most energetic particles, you really have very tightly focused beams, at least in these two-dimensional simulations. And this is important because for relativistic particles, the radiation that the particles produce is always in the direction of propagation. So this anisotropy of the particle distribution translates immediately into the anisotropy of radiation. And in particular, one can see the following picture. Let's say if you have that the observed signal depends strongly on the orientation of the observer, orientation of the line of sight relative to the reconnecting system. So for example, if you have a distribution of particles, the overall distribution shown in this blue line here, right? The distribution seen in a given direction depends on well, this is actually photon distribution. So this is synchrotron photons that they produce. Depends on the orientation of the observer. So if you put an observer here, then the observer will see the same low energy emission as isotropic, but much reduced high energy emission. However, if the observer is lucky and sits here at this moment of time, then the high energy radiation that this observer would see is highly enhanced. So this is what we call kinetic beaming, and it has this effect has very important implications for astrophysics in terms of estimating flare energetics, that you no longer divide by 4 pi, and also evaluating the statistics of occurrence of flares, because basically you don't see flares all the time when they occur, but only when by chance a beam sweeps past your line of sight. So going back, for example, to the Crab Nebula flares, if we see a flare, high energy flare, lasting a few days once a year, then what one may think is that perhaps flares like this actually occur all the time, but we don't see them most of the time. We only see them occasionally when we are lucky. All right. And then this, these beams, they are not stationary. They are swaying from side to side in the reconnection plane, as you can see in this animation, in this movie. And this results in a rapid variability of the emission, seen again by an observer looking at the system from a fixed line of sight. So here, for example, this is the overall light curve, this green line here. That would be the isotropically averaged light curve. But an observer looking at this direction or this direction, we'll see a much spikier, yes, signal.
You have a relation between solid angle and lens factor. How far away from Earth would a spacecraft have to be to see a significantly different light curve?
How far from Earth?
Yes.
So if you have two spacecraft looking at like stereos, like solar stereo, right? Well, I don't think that's feasible. Well, the angles we are talking, I mean, these are simulations. We don't know what really happens, but well, well, still, I mean, the angles we are talking about are still very large. I mean, look at, so if you look at these angular maps here, for example, right? From here to here is 360 degrees. The size of this is, you know, many, many degrees. Right? So from the Crab Nebula, it's a very large spot. So I don't think. All right. So so applying this sort of thinking to Crab Nebula flares, this is the result of simulation that were conducted by Benoit Cerruti, specifically with the parameters of the Crab Nebula. He basically sees the same picture, and he sees that for an observer located at some lucky location, one can indeed see emission extending well past this sort of classic standard synchrotron photon energy limit of 160 MeV. And one can, in fact, even fit the observed spectra if one wants to. All right. Okay, so this brings me to the end of my talk. I just wanted to say a few words about the future outlook. I think, first of all, that radiative reconnection is important not only for Crab flares, but also for a wide range of other astrophysical systems in high-energy astrophysics. And as I mentioned, Crab is actually the case where it is the least important. If one gets closer to the pulsar itself, in particular near the light cylinder of, say, the Crab pulsar, the magnetic field is so much more intense that radiation feedback, radiation reaction affects not only the highest energy particles, but all the particles. So the entire reconnection process is subject to strong radiative cooling. In corona of accreting black holes, magnetic fields are also important, and also inverse-Compton cooling is very important and may affect the acceleration of high energy electrons. And the same thing happens in gamma ray burst jets. Now, we are also expanding our technical capability, so at least we have plans to do so. The most important thing, I would say, is the diagnostics. The diagnostics is as important as doing simulations themselves, and it takes more time and more effort. It's really very important to be able to look at these complex systems from different points of view. That requires a lot of effort. But then we also will be adding new radiative processes, such as Bremsstrahlung, synchrotron self-Compton, and maybe collisions pair creation. And also, this code, Zeltron, can be applied, and in fact is already applied to other plasma processes that are relevant to high-energy astrophysics, not just reconnection, but let's say turbulence or shocks. All right, so I will stop here with the summary. Basically, I want to say that the future of radiative plasma astrophysics is bright. Okay, thank you. Right. Moves them.
What sets
right.
the amount of time that they're being accelerated for before they're pushed out by the reconnected field?
Well, they're pushed out. It's a in real large systems, there is not one X point, but there are many X points separated by these plasmoids, and particles can get trapped into these plasmoids. Let's see, what sets the time? It's basically, I think, depends on the initial position and initial velocity of the particle when it enters the reconnection layer. Right, so if you put a particle right at the center with 0 velocity, it will continue definitely. But if it's somewhere else, it will be the force with which it is being deflected in the what we call x direction is proportional to x itself, actually. So of course, I actually don't know, but I actually think that it's the former. It's the first of these. So
But that should determine where the peak is. There should be then a distribution of particles coming from different X points.
so they're highly. What we see here is one thing to take into account is that the effect is very dramatic. So you see a very large enhancement if it's along your line of sight. If it's slightly off, you'll see a weaker event. And in fact, we do see weaker events. In particular, people have, for a long time, regarded the Crab Nebula as a standard candle, constant emission in gamma rays. But then after the discovery of these flares, which of course completely broke down this picture, they started looking back at the data, and they do see that there are some fluctuations all the time. But what's important here also is that at other wavelengths, the signal will be hidden by emission coming from the rest of the nebula. So the reason why we see these MEV, 100 MeV or GeV flares is because they fall into the spectral region where we don't see the nebula. The nebula is much dimmer in general. So if you have a weaker event producing light at lower wavelengths, then it will be perhaps hidden.